Okay, so I think everybody knows Dr. Guzik, but I thought I'd give you a brief introduction, and I would also a couple of matters of points of procedure. If you would like to see his CV and application materials, again, let me know. I do have a bunch of teaching information I'm going to send you. I haven't had time to actually sit at my computer and do any email, but I'll get that out sometime tomorrow. Next Wednesday is the faculty meeting. Everybody hopefully has on their schedule where we're going to talk about all this. And then for our colleagues who aren't here, we are making a videotape, so help spread the word amongst your colleagues who aren't here about that as well. And Sona and I will email about that. Okay, so Dr. Guzik got his PhD in Aerospace Engineering and Science from the University of Toronto, and his master's from Laval University, and his BE from Royal Military College. All of those degrees are in mechanical engineering. He's been here at CSU with us as a sophomore researcher since August 2012. And before that, he was at the Lawrence Livermore National Lab for roughly 3 years as a postdoc and higher level staff there. And he's going to talk to us about his CFD research.
Actually, my last degree there at Toronto was in aerospace engineering, so hopefully that makes me qualified to talk about aerospace propulsion. My talk today is next generation CFD for aerospace propulsion, and I just want to, I'm just going to basically give some idea of what that means. A basic outline, I'm going to actually do a pretty lengthy introduction just on the history of CFD and to kind of give you some idea of where I'm coming at this from. Then I'll talk about what next generation CFD is and what's the goals of our laboratory here at CSU. The technical content of my talk is the finite volume methods we're using on map grids, just how we implement those, and the procedures we're putting in right now to verify and validate our algorithms. And that's, you can think of that as the results kind of portion. Finally, I'm going to talk a little bit about application performance then in the technical part, and then go into a little bit of some of the concepts related to teaching that I'm taking from my computational work and trying to apply to the undergraduates, and just kind of give you an idea of that. Sue mentioned that there's a document, and it repeats some of the information I'm going to talk about here. Finally, my collaborations, and then a quick conclusion. So what do I do, or what is my purpose? The story behind, actually this cartoon reminds me to, I was hoping to keep this talk informal, so please if you have any questions as we're going along, feel free to ask. So the storyline behind this cartoon here is Gary Larson, the author of Far Side. He knew a woman once who had a boyfriend, and the father of the woman was berating the boyfriend. His name was Edgar, telling him, "Edgar, your problem is you have no purpose. Everybody has a purpose in their life, and you just haven't found yours yet." And so in true Larson style, this is how he imagined Edgar finally finding his purpose. My purpose is a little bit more well-defined, I'm happy to say, but it was a little bit more difficult to achieve. So as Sue said, I got my PhD from University of Toronto in aerospace engineering, and then went to do a postdoc at the Center for Applied Scientific Computing at Lawrence Livermore National Lab. And what exactly do I do? What is my purpose? I make engineering tools. That's kind of my mission. That's what I do. And I work in the field of computational fluid dynamics. So we all know fluid dynamics. The equations that govern fluid flow are very much mechanical engineering. How can we explore these equations? We can use analytical methods. We can use experimental methods. And with the last couple of decades, we can also use computational approaches. So solving the mathematical equations on computers and looking at how the fluid behaves there. The standard technique for that is so how do we solve these equations? We solve them at discrete points in some domain, and that usually involves creating a grid. So there's a grid here showing wrapped around some geometry. This is actually from Dimitri Mavropoulos, who's up in University of Wyoming. And it's quite nice to have him nearby because he has a lot of experience. Spent 16 years at NASA and is doing a lot of great work on rotorcraft and real aircraft geometries. But so you create some grid, and then you solve your equations at these discrete points. And throughout my talk, we'll kind of go into detail of what that entails. On the right is just shown then, a simulation of, so what do we do with computational fluid dynamics, especially in propulsion, while we try to solve some kind of turbo machinery. And we see that here with the simulation that's been done by Nate Spots in our group. And so now I want to talk a little bit about the history of CFD. So where did it start? Where are we at right now? And actually, I've taken these slides from a talk by Anthony Jameson. Partially, my intent is actually to appeal to authority for these slides. Jameson is actually a quite internationally recognized expert in CFD and has been involved pretty much since the beginnings. So the timeline here, you can really see that it kind of takes off at the same time that digital computers take off. I mean, yeah, we had digital computers maybe back in the 50s, but by the 1960s, more and more people can use it. And it was really in the 1980s to 1990s period where the theory behind the CFD that's mainstream nowadays really took off and was really developed. And here you see all the big names. Well, Godunov was earlier, but Van Leer, Rowe, Jameson again, Harton. I mean, these are where the main contributions to CFD were actually made in this period. And so it seems like, what's happened since then? So I think this is a little bit self-serving, what Professor Jameson has written here, or Jameson has written here. And it's actually next generation CFD that's kind of taken off between 2000 and 2010. And indeed, I would agree that aerodynamic shape optimizations or any type of multidisciplinary, multi-physics, coupling different kinds of solvers together, that really was the domain of 1990 to 2000. And just a quick illustration of, so how is this practically used in industry? And this is just, Jameson worked quite a bit with Boeing, and this is kind of his outline of how CFD has helped them with their design of aircraft. A couple things to note. One is, the main idea here is that if you can do the experiments on the computer, it reduces the amount of testing you have to do in the laboratory itself, so hopefully it'll save you some costs. And perhaps you can even do more high fidelity designs on the computer too, especially if you can couple your CFD solver with computational optimization. But a kind of curious thing is that, the state of the CFD software, TL and S, that actually means thin layer Navier-Stokes. So they're not even solving the full Navier-Stokes equations. Even up to 2000, most of their designs are still using fairly older technologies, things that were developed in the 60s, or sorry, perhaps in the 70s. So that's kind of interesting. So, a very conservative kind of industry. And, they're just kind of transitioning right now at this time to even being using full Navier-Stokes solvers to do the design of their aircraft. And when we do work with Boeing, it's kind of in this area, working with their codes. Overflow is one that they love to use. So when we collaborate with Boeing, that's kind of what we do. But so where's my purpose? Where do I live? I'm kind of off in this field here, sort of developing the next generation of software coming up. The keyword here is adaptive grid, is kind of these new technologies that are coming online. So that's one thing I'm going to talk about a lot today, or you'll see a lot of. And then these are his summaries and conclusion. It's probably the most informative of his slides. The first thing is, why did mechanical engineers get involved with CFD and kind of drive the initial development of the technology forward? It's because they had to solve this problem, or at least his opinion is, it's because they had to solve this problem of transonic flow across a wing. And what that means is as the airflow goes over the top surface of the wing, it of course speeds up, and at the speeds the aircraft are flying, it can get very weakly supersonic, and you can get a weak shock forming on top of the wing. And that can have a dramatic impact on the lift and drag characteristics of your airfoil. So it was a difficult problem, and they needed computational tools to solve them. That's what motivated to really develop all these algorithms, and that's why mechanical engineering kind of took hold of this problem and drove it forward for the first couple of decades. But then something, between 1980s and now, something interesting happened. Well, he says, maybe for the last 15 years. That's kind of the state of the art stalled. And these second-order accurate finite volume methods solving the RANS equations kind of became the norm for doing any kind of research, and there was not really any advances since that period. You look at all the standard solvers out there, Fluent, CFD++. These are second-order accurate, and they're solving the RANS equations. What does RANS means? That's a turbulence model. So when we solve the Navier-Stokes equations, those equations themselves hold the full physics of turbulence, but there's something called an energy cascade. So you can imagine these large turbulent motions, they kind of get to smaller ones, and smaller ones. At the very smallest scale, those turbulent eddies are dissipated then by viscosity. So if you want to solve turbulence with a CFD solver, you have to model that very finest scale. And that's called DNS, a direct numerical simulation of turbulence. Very expensive, though that scale is very, very small, and we can't do anything practical with DNS nowadays. You can't do even a car with DNS. So there's models involved. RANS is where you kind of model all the turbulence. You take all the unsteady characteristics and you make it just steady state. So it's kind of the opposite extreme from DNS. Nowadays we're looking at intermediate technologies, LAS, where you model some of the, you simulate some of the larger scales of the turbulence and you only model some of the smaller scales. And so, but what's the problem with stalling at second order finite volume? It really limits what you can do in terms of complexity because, as Jameson says, these methods cannot predict complex separated, unsteady, and vortex-dominated flow. And I'm going to add to this turbulent combustion, which is very poorly solved by any kind of second order method. And so there is a need then for higher capability algorithms, ones that are more accurate and can appeal to higher fidelity physics models to get better answers for the simulations. LAS is a big thing we want to see starting to be applied more regularly to industry. Higher order methods is a lot of what my talk is about, and at some point even DNS. And kind of going along in this field is you have to keep up with the computers too. If you don't, you're kind of going to lose track. And I'm going to talk about that at the end. There's another revolution kind of coming in computer architectures. So my focus then is on next generation CFD software, the stuff that's coming up next. And you can kind of characterize this in two ways. One that a lot of you here are very familiar with, which is actually increasing the usability of the software. So right now, if you're going to do a simulation with a structured grid or an unstructured grid, you might spend a lot of time just creating the mesh, those grid points where you're going to solve your equations. An engineer could spend up to a month just generating one high quality grid for a problem. Takes a lot of time. So part of next generation, one approach or one thing they're going after is actually increasing the usability, reducing the burdens on the engineer to get a decent answer out of CFD software. Converge is an excellent example of that. It's probably less accurate in some sense than what you would get with kind of the older generation stuff, but it's very usable. You just throw in your geometry and it automatically will mesh it and even do some adaptive mesh refinement. But really what I'm focused on is kind of another idea, which is higher accuracy and performance from these CFD solvers. So we're still going to keep them just as difficult to use, but we're going to increase their capability in solving certain types of problems. And I want to give an example of one kind of problem that actually coming from Boeing now. Because everybody's kind of in, we're pushing optimization further and further, higher efficiency, higher everything. Of course, we're running into more challenges. So part of what the next generation CFD is for doing off-design type studies. You're not operating at your ideal conditions anymore. Can you handle these kinds of cases? One of the problems they're encountering is to get more efficiency out of their engines, they have to increase the mass flow rate through them. So the fan itself on the front keeps going bigger and bigger. The bypass ratio keeps going higher and higher. Well, of course, your blades are getting longer and they can flex more then. So they used to have requirements that, they would say, okay, the flow coming into the inlet of the engine had to be uniform at cruise conditions. Now they're saying you can't really have any distortions at any time. The problem that we're interested in, or this is showing here, is this simple case where your aircraft's sitting on the runway and it's ready to take off, and the pilot hits the throttle and starts cranking up the engine. So they start ramping up and drawing more and more air through the engine. Well, the problem is if you have a crosswind across that inlet, the air can separate coming off the tip, and it'll cause turbulence, which will then move into the engine. And so you get highly distorted flow, and that's what the fan blades see. And that could really reduce the life of the engine. And of course, the consumers, they don't blame the engine companies, they blame Boeing when this doesn't work. So this is a serious problem that they have. The eddies you see on the outside, that's actually not the problem. I mean, it's a nice picture, but it's not the problem we're interested in. We're interested in what's going on inside this fan. So one of our students Nate Spots, is doing some work in this area. Here we see a distorted flow pattern coming into the inlet. And what he's trying to study here is what is the actual fluid, how does that affect the flow behavior inside the fan? What this research project is about is actually designing models for this fan so we can actually take it away, but still get some representative physics governing what's happening at the fan and how that affects the separation of the flow upstream of the fan. Nate did a tremendous job in making this movie, I think. It's quite fascinating. And this is all with, this is the old stuff, right? This is your standard second order finite volume. One question to ask is, we can always make pretty pictures with CFD, but is it correct? Is this actually what's going on? In this case, yes, we have fairly high confidence in this simulation. And that's because we have a fairly simple distorted flow coming into the inlet. But if I was actually going to try to solve the real problem, the actual separation of the flow, actually our standard second order finite volume methods cannot handle that problem. So why is this kind of problem important? It's because we need these higher level capabilities so we can better optimize our aircraft, so we can better improve the fuel efficiency of them. And why is this suddenly so challenging? Why can't we do this with standard second order finite volume methods? There's a lot of physics that's going on here. For one thing, even if the aircraft is stationary and you just have a crosswind going across the inlet, as it spools up and the air kind of wraps around the lip of that inlet, it can go to supersonic speeds. So you can get a wide range of Mach numbers in this simulation, all the way from 0 up to supersonic flows. And you have to be able to deal with that. The flow is transient because there's hysteresis in the, or hysteresis, sorry. Yeah, I've obviously made that mistake before. In the engine, at which the separation occurs. And that depends on whether you're ramping up the engine or spooling it down. So that'll change where your separation pattern occurs. And what that means is you actually need a true unsteady solver. You can't appeal to any of these steady state solvers to handle this problem. The turbulent flow itself, it's complex, three-dimensional with separation and reattachment. And that's even getting that is not sufficient. You have to actually correctly model where the flow transitions from laminar to turbulent. Finally, if you do all this research without the fan in there, the results you're going to get are going to be too pessimistic. So you actually need to understand the influence of the fan itself, meaning you need either all that geometry in there or you need a good model for that. And I should say even the simulations that I just showed you, that takes about 10 days to run on the cluster we have here. So they're very expensive stuff, difficult to do design work with. And what's our approach to solving these problems? So we have an in-house CFD code called CHORD, which is based on an application framework, Chombo, developed at Lawrence Berkeley National Lab. The base code is a framework designed for doing parallel adaptive mesh refinement. Our application on top of that is designed to do engineering flows, so to do the Navier-Stokes equations with reacting flows. So hyperbolic terms, or the inertial terms, the viscous terms, and reactions. And we're also, one of our main contributions is just a capability to handle more complex geometries. So DOE labs, they like to do these, these physics studies, which are often done in a very simple Cartesian box. Just do some, I don't know, neutrons or something flying around. Your DOE labs always doing nuclear work. But when it comes time to do engineering, you need to resolve all those geometries. And they're kind of behind in that context. That's a lot of where my research effort is focused. So CHORD is based on Godlov-type finite volume methods and features. These are the key technologies: adaptive mesh refinement, mapped grids. That's the technology I'm going to talk about today for handling complex geometries. It's got fourth order accuracy in both time and space. There's opportunities for fine-grained parallelism and massive concurrency in a modern computer node, so it's ideal. Other approaches, they'll figure out how to get those working on the new computers too, but first of all, these structured grid codes is where everybody's kind of targeting their effort. And so we're kind of ideally situated for that. And that includes the way we kind of do our stencil computations. We always use a Cartesian grid for doing our derivatives, and that means they're very fast in our code. The key detail here is really fourth order accuracy in time and space. And the problem here is that this makes everything else more challenging. You can do adaptive mesh refinement, map grids. It's been done all at second order. But once you try to raise this to fourth order accuracy, there just become more and more considerations that you have to worry about. And speaking of fourth order accuracy, why is this so important? What do you really gain? And you're going to see a couple of these plots today during my talk. What this is plotting is, along the bottom is the one-dimensional mesh size. So I'm doing several simulations, one with 16 grid points in a direction, one with 32, 64, 128, and 256. And then I plot the error in my solution. So I'm probably doing this with some simulation that I know the exact analytical answer to. Then I'm solving it numerically and seeing what's the error in my solution compared to the theory. And I plot this. And what I should get when I have a log-log plot is the slope of my curve, if I connect all these points, should be the order of accuracy of my scheme. And so this is for Couette flow, actually. So it's a viscous solution. Here we have a slope of 4, and we see we're actually getting a little bit of superconvergence in this problem. It's closer to 5, these curves. But what we've shown here is a slope of 4 and a slope of 2. So a second order code would have this kind of slope here. Now the question to ask is, if I need a given level of accuracy out of my solver, what kind of mesh do I need to get that level of accuracy? So this red line here is kind of a baseline saying I need my solution error, for whatever reasons, maybe just for the physics I'm trying to solve, down to 10 to the minus 10 in terms of error. So if I'm running a fourth order code, I can get away with a mesh size of about 64. If I'm running a second order code, I can get away with a mesh size of 256. So I need a much larger mesh to solve it at second order accuracy. So then you could...
In 3D, that's cubed.
Well, is it cubed? Actually, it's core to the fourth power. Yes, quartic. Because time as well. So time decreases along with the mesh size, the time step we have to take to solve these. So chances are, at least for an unsteady simulation, yes. So actually it's going to be 256 times slower to solve this on a second order code than with a fourth order code. What that means is that if we actually keep our mesh size the same, we can get much higher fidelity out of our solution. We can use much higher fidelity physics models and actually try to tackle these problems that we need next gen CFD for. And actually, so I'm working, what I do is I work on creating this tool of next generation software, but we have a goal in our group too. And what that is really to do a full simulation of a gas turbine engine within about 10 years. We don't get funding to do this, but this is kind of, we would like to be the ones that first attempt this. That's kind of our, something that keeps us, really motivated. This is a grand challenge in mechanical engineering and has not been done. Stanford kind of attempted it back in the 2000s, but there are a lot of approximations in their solver. It wasn't a complete coupled simulation, or a full simulation. They actually coupled several different solvers together to get that scheme working. And perhaps most importantly for industry is we want to do this on a $100,000 type petascale computer. Well, we can do the components at petascale. You'd probably need an exascale computer to actually do the full gas turbine engine. But this whole concept of $100,000 petascale, what does that mean? So petascale capability, I'll talk a little bit about this later, but that's what you needed to kind of do a laboratory size industrial burner. If you wanted to solve that with CFD, you need kind of the order of a petascale to do that. So doing this fan with LES, that probably takes a petascale computer. Doing the combustor probably takes a petascale. You add all these components together, and it might take up to an exascale. What you can do with a petascale is it's been shown that you can really go down and do some really high fidelity physics models. So it's really quite attractive. But of course, petascale back around 2010 cost $100 million. But as DOE pushes towards a $100 million exascale computer, so a 1,000-fold increase, that means we just buy a couple of nodes of those, and we get a petascale computer that's actually, we could buy that. Woodward could buy that. You could buy more than that, several of those. And then this kind of next generation CFD becomes really attractive both to academia and industry. And everybody's expecting profound breakthroughs from this kind of capability. And so that kind of concludes my introduction, and now I want to get into the technical part of just how do we solve these equations then, and what are we up to in terms of algorithms. So what we're solving is some kind of partial differential equations that represent fluid flow. Of course, what this is mass conservation, momentum conservation, and energy conservation. And all this stuff is encapsulated in this one equation. So U is a vector, that's my state, and my terms in there are, for example, density, momentum in my various directions, and the energy in my problem. And then the other terms govern the evolution of these properties in the area that I'm studying. So we're using a finite volume method. What that means is, it's kind of like if you look at undergraduate fluids, you integrate these equations at some large scale, and you then can apply these conservation laws on kind of a macroscopic scale. We kind of do the same thing, but at a very small scale, and then piece together a bunch of these small scales to do our simulation. So this starts by integrating over some volume in space. We integrate our equations, and this gives us the integral form of the equations governing fluid flow. What happens next? So if nabla here is a derivative, what's the integral of a derivative? They cancel out, right? So that's kind of what's going on here. This is actually the application of the divergence theorem of Gauss. What it means is, it's the same kind of idea. The integrals kind of cancel out, but what happens is instead of integrating over my volume, I don't have to integrate this term over the volume. I only have to integrate it on the surfaces of my volume. So I kind of get a one codimension reduction in the locations where I have to integrate. When we do that, and if we then replace the integrals of these quantities over the surfaces, over the volumes with averages, then I get this resulting equation here. And what does this mean? So think, for example, in terms of just mass conservation. So here's my little volume here. I'm going to have some quantity. The density of my fluid inside there is my mass. These terms, F and G, are the flux of that mass through the surfaces of this volume. So I could have a little bit of flux moving out one edge. Then how does that change my density inside my volume? Of course, if the net mass flow is going out of the cell, then my density is going to decrease in that cell. That's all this equation is really saying. So it's saying on the cell, there's an average of my solution state inside the cell, and these terms are the fluxes on the faces of mass, momentum, and energy flowing through the faces of my cell. Why do we have F and G? We like to separate these out because F is our inertial terms, so the Euler equations. G adds in the viscous terms required to solve the Navier-Stokes equations. For the hyperbolic terms, we solve them using a Godunov-type finite volume method with limiting and upwinding. And G is also done with a fourth order stress tensor to get the viscous terms to fourth order accuracy in space. To get fourth order accuracy in time, we use a method of lines approach, which basically involves, once we get our semi-discrete form, this actually looks like an ordinary differential equation, right? So it's not partial anymore, which means I can apply just a solver for ODEs like Runge-Kutta. That's what it's designed to do, and get fourth order accuracy then in time. Done, kind of. That's good for Cartesian meshes, but we need to handle complex geometry. The technique we're using for that is actually to map our curvilinear grid in physical space into a Cartesian grid in computational space. So remember I just said back here that if I was doing Cartesian grids, I was done. Well, if I do this kind of mapping approach, what it means is I can use all the theory I developed previously, do that on my computational grid, and still have it apply to this twisted grid that's actually kind of wrapped around some physical geometry and physical space. All it really means is I have to introduce a few terms that we call metric Jacobians, or metrics, the geometry metrics, which kind of describe that mapping. So J is really your metrics Jacobian. All that says is what's the difference in the cell size between my cell in computational space and physical space. Let me show you how these are applied. So again, here's our equation that we just saw, the integral form of the Navier-Stokes equation applied in physical space. When we switch to computational space, it's just really a change of variables. You can find this in any undergraduate mathematical textbook. But you can see everything looks the same. All that happens is that this term J appears in my solution state, and an NT appears that multiplies my flux terms. So then we then go through and apply the divergence theorem of Gauss. So now instead of an integral over the volume of my cell, again, I have an integral now over the surfaces of my cell. So my flux terms are now evaluated on the surfaces, exactly the same as before. And then I replace my integrals again with averages, resulting in a very similar equation to what I had earlier, except now there's a J here and still these NT terms multiplying my fluxes. Not really too bad. How do we do this multiplication? You have to be careful. You can't just multiply two vector terms together, not if you expect fourth order accuracy and you're working on discrete meshes. So we use this formula here, our product rule formula, we call it. So the product of NT and F and the average of that on the face, the key idea here is that you can't just, if there was a point values, yes, you could just multiply them together, but when they're averages over the face, you cannot. You have to be a little bit careful what you're doing. So to do this product rule, to get the average of the product, we multiply the two values. That gives us second order accuracy. Then we have to add in these derivative terms to raise it to fourth order accuracy. Where does this come from? Taylor series expansion on Cartesian grids. But now there's some little details that we have to worry about. One of these is, imagine you have, in your physical space, you have some kind of wrapped grid, and you have just a constant vector field on it. Your solution's exactly constant. What happens when I put this into computational space? I twist my grid a bit. Well, I'm suddenly going to see variations in my solution that aren't really there. So I have to make sure that I design my scheme so it preserves that. It preserves a constant vector field. And that's very important for doing these map kinds of schemes. This formula here is actually kind of problematic then. So assume F is constant everywhere in my domain. Well, this term, and we really want this, these fluxes then to cancel out. So this term, if F is constant, obviously goes to 0. I'm taking the derivative of F. And then I just have to worry about the leading term up here. And what this is saying here is that we need to devise methods then that ensure that N times F is free stream preserving. So when I